All right, hello everybody. So let's review for exam 2P by going over some reaction kinetic problems. Okay, so let me see what we have here. So this is schema 2 review, and let's start with first question over here. We are given the overall reaction, okay, or it can be steps, so we can find the overall reaction from the steps or something like that. And then they are asking us to determine the Venn diagram. So to do that, we need two things. We need the picture. Okay. We need to determine the relative potential energy, and then we determine the relative entropy. Okay. So when it comes to relative potential energy, it's all about the bond strength. We have all AB bonds on the reactant side. Therefore, we're going to have a lower potential energy on the reactant side. And then we have some AA bonds on the product side, meaning they are going to be weaker, okay, weaker, and therefore the product side will have an overall higher potential energy. Okay, so we can just indicate that. So the reactants have a lower potential energy compared to the products. Okay, and then the entropy. Entropy is determined by mainly the gas molecules. We have only 2 gas molecules on the reactant side, but on the product side, we have 4 gas molecules. Because we have more gas molecules on the product side, we have a higher entropy on the product side compared to reactants. Therefore, we can say the relative entropy is greater in the product side compared to the reactant side. Okay. Therefore, the products have a higher entropy and higher potential energy. Therefore, it looks like our graph, our Venn diagram is this. Okay. And moving on to the next question. How does the equilibrium constant of the dry reforming process changes as a function of temperature? Okay. So now what we notice here is the delta H. If you think about the delta H, or the change in potential energy, is going to be positive. Okay, when you go from reactants to products, the enthalpy or the potential energy increases. Therefore, delta H is positive. And also, products have a higher entropy compared to the reactants. Therefore, you are increasing the entropy as well. Therefore, delta S, or change in entropy, is positive. Okay, and if we have this situation, okay, this is product favored only at high temperatures. Okay, because the products are favored by the number of configurations or the entropy, but not by the potential energy, because products have a higher potential energy. Therefore, if you want to favor the formation of products, you have to increase the temperature. All right, so product favored only at high temperatures, meaning reactant favored at low temperatures. Therefore, K must be less than 1 at low temperatures. Okay, so that means reactant favored at low temperatures, and at high temperatures, K is greater than 1. So this region, K is greater than 1, meaning product favored in that region or in at high temperatures. So that should be your graph for that. Okay, remember one thing: K greater than 1 means product favored, and K less than 1 means we have more reactants than the products at the equilibrium, means reactant favored. Okay, this is a reminder about what is involved there. Okay, and moving on to question 3. We're still on thermodynamics here, but usually this exam is more focused on the reaction kinetics, right? But still, we need to know this background on thermodynamics. But let's do this question as well. All right, which of the following graphs best represents the change in concentration of reactants and products as a function of time at high temperatures during this reaction? So we know that delta H is positive for this. That means it is product favored only at high temperatures. because delta H is positive and delta S is positive. If they both have the same sign, that's going to be a temperature dependent reaction. That means the reaction direction depends on the temperature. And then in this case, it's going to be product fluid only at high temperatures. So high temperatures, okay, you should have more products than reactants, okay? And then therefore, if you look at any of these graphs, the only graph that has high product concentration at the equilibrium is this second graph over here, okay? So this is a reactant favored situation, okay, because K is less than 1. And then here is the only product favored situation. Here is neither product favored or reactant favored in this graph. So therefore that is out. And then this graph, again, it's kind of weird. It initially decreases and then achieves a plateau. And then this is something else going on here. So that is out as well. And also at the end, and there's no equilibrium. So that is out. That's a weird concentration versus time plot, the first one. Therefore, the correct answer must be option B. All right, the next question, how many reaction intermediates are involved in this mechanism? So intermediates are produced and consumed. You see that C is produced and consumed over here. Therefore, that's 1. And then we have hydrogen, okay, it's not consumed. And then we have CO, seems to be a product. And then oxygen is also produced and consumed over here. And then that's all I see. So everything else, okay, you see that if you add the left-hand side of the arrow, you only get these 2. And on the right-hand side of the arrow, we have 2 COs and then 2 hydrogens. So that's it. Okay, so we have 2 intermediates, carbon and oxygen. Okay, so this guy and then this oxygen. So it's going to be 2, option C. Moving on to see question 5. I need the mechanism. All right, so let's take another picture. Okay, what is the rate law predicted by this mechanism? Remember, the rate of the overall reaction is determined by the slowest step. Okay, so if you write the rate law for the slowest step, that gives you the rate law for the entire reaction. Only thing is, if that rate law had intermediates, we need to replace that to get replace that intermediates with something measurable by going back to the previous step where that intermediate was generated. Okay, just keep that in mind. And then here the first step is the slower step, and that tells me that rate law is equal to a rate constant times the only reactant here is CH4. Therefore, that's going to be it. Okay, this should be the rate law for the overall reaction. Okay, and then this rate law, that's it. Okay, so that's option A. Which of these graphs represent how reaction rate changes with the concentration of CH4? So rate and CH4 concentration are directly proportional to each other. When one increases, the other one increases linearly. Therefore, it looks like this is the valid answer here. All right, moving on to question 7 and 8. Okay. All right. Which of these graphs represents how the reaction rate changes with the concentration of CO2? So again, just to remind us, the rate law for this was rate is equal to rate constant times CH4 concentration. And then they are asking about CO2, which is the other reactant. You can include that here, okay, CO2, but it is going to be 0th order, okay, with respect to CO2. That means the reaction rate does not depend on the CO2 concentration. Whatever the concentration is, rate is going to be the same. if it is 0th order. So therefore, the correct answer is option C. Next question, which of these graphs represents how the concentration of CH4 changes as a function of time? If it is, so now we know that it is a first order reaction with respect to CH4, okay? And the idea is the exponent for CH4 is 1. It is implied already. That means it's a first order reaction. If it is a first order reaction, what is going to happen is concentration. If you plot concentration versus time, it's going to change like this. Okay, this is for first order. Okay, and then something like this would be for 0th order. Okay, the idea is the slope or the rate of the reaction does not change with time. Even though the concentration decreases, the rate is the same. And that is what we have in 0th order reactions. And if it was second order, just to review, concentration versus time should be more dependent on the I'm sorry, the rate of the reaction is extremely dependent on the concentration of the reactant. As a result of that, the decrease of the concentration is going to be much steeper compared to that of a first order reaction. Second order. Right. Now the thing is, we see that it's really hard to distinguish between first and second order, and that's why when we need relationships between concentration and time, we go for integrated rate laws, which is going to give us linear relationships. Okay, we'll get there when we get there. I'm pretty sure there are questions like that in this exam as well. All right, now moving on to questions 9 and 10. Okay, let's do that. How would the addition of a catalyst affect the extent and rate of this reaction? Adding a catalyst will lower the activation energy barrier by providing a path with a lower activation energy barrier. And as a result of that, the rate constant increases. And therefore, the speed of the reaction or the rate of the reaction increases. Extent is not affected. All right, it would increase both the rate and the extent. No, it would increase extent. No, it would increase the rate, but not affect the extent of the reaction. So we should go with that. No, I cannot provide that. There you go. See. Okay. So, all right. So moving on to question 10. Then I think we're going to get data here now, which is great. Okay, I'm going to have my Excel or calculator ready now because we're going to deal with the data. Okay, now we're given data, the time and concentration data. This is what we do in a regular kinetic experiment. Okay, we measure concentrations of reactants and then the time. Okay, and then the question is, at what temperatures should this reaction be performed to ensure that the significant fraction of CO2 is actually captured by the process? Okay, we will read a little bit more. Oh, give me a second. The following table is all right. Now it doesn't seem like it has to do anything with this data here, but the thing is, they're asking about the temperature, right? At what temperatures should we perform this reaction to capture more carbon dioxide? That means to have a product favored reaction. Okay, you see that we have delta H and delta S negative for them. That means this is a temperature dependent reaction, and it's going to be product favored only at low temperatures. Now that means there's switching temperature around. I mean, after a certain temperature, it's going to be reactant favored, and below that temperature, it should be product favored. So we need to determine that. Do that, we can use this equation. The switching temperature is equal to delta H over delta S. And then that is going to be minus 109 kilojoules. I don't think that mole is correct here, but anyway, kilojoules divided by 0.186 kilojoules per Kelvin. So kilojoules cancel out. And if we do this, why I pulled out my Excel. We do this on Excel. What we have is 109. This is the minus value as well. That's why it's going to be positive. 109 divided by 0.186 is 586. This is going to be 586 Kelvin. Okay. So again, this is product favored only at low temperatures. So meaning, if you have this graph, K versus temperature, here's one. So at low temperatures, it's going to be product favored. That means K is greater than 1 at low temperatures. And then at high temperatures, K is going to be less than 1. Okay. So this switching temperature over here is 586 is Kelvin. Okay. And if you want me to remind you about the delta G versus temperature as well, here's delta G, here's 0. Delta G is negative at low temperatures, and at high temperatures it becomes positive. Okay, so for product favored, to be product favored, delta G must be negative. Okay, anyway, this is 586. All right, now anyway, so we need to be below 586. Okay, to be product favored. So that should be option B. All right. Moving on to these questions. Okay, so one thing to learn from that question is that sometimes we can get bogged down by the information given to us. We are given some data, but for that previous question, we did not have to use that data to determine the answer to that question. So sometimes you should be able to see the forest from the trees. Okay. Anyway, at what temperatures can we expect the rate constant for the forward reaction to be smaller than the rate constant for the backward reaction? Okay. At what temperatures can we expect the rate constant for the forward reaction to be smaller than the rate constant for the backward reaction? Okay, now this is something we did not specifically talk about in class. Okay, but if you think about it, now if it is producing when we have the equilibrium, okay, it's a dynamic equilibrium. All right, so that means the rate of formation of the products is equal rate of formation of the reactants. Okay, now the thing is, if you have more reactants at the equilibrium compared to the products, that means the reverse reaction rate must be, or the rate constant for the reverse reaction must be greater than that for the forward reaction. Okay, and then that is what it's asking here. Okay, so in this case, we are told that the rate constant for the forward reaction is smaller than the rate constant for the backward reaction. So you know what? I'm gonna mention this here so that we can learn something. So we have the rate forward. Okay, rate forward is rate constant for the forward reaction times the reactants involved in the forward direction. Okay, so let's say the reactants for the moment. Okay, and then we can determine the rate for the backward reaction or the reverse reaction. There should be rate constant for the backward reaction times the reactants for the backward reaction, which is going to be the products. Okay, should do some exponent, which we don't want to worry about for the moment. Okay, this is my 1, this is my 2. At equilibrium, okay, we know the rate forward is equal to rate backward, meaning Kf times reactant concentration to the power of something is equal to Kb times product concentration. Okay, now if you rearrange this, we see that we can have constant on one side, Kf divided by Kb. I just move the Kb to the left hand side, and then I'm going to move my reactant to the other side. Is equal to that. We know products over reactants is the equilibrium constant. Okay, so let me rewrite this here so that we can say it clearly. Kf divided by Kb, or this is a rate constant for the forward divided by rate constant for the reverse is equal to the equilibrium constant. Okay, now we know this is a temperature dependent reaction, okay, because of these values. At high temperatures, K is less than 1. Okay, at high, I'm going to write this here and then I'm going to erase before I move to the 1. At high temperatures, K is less than 1, meaning your denominator value must be greater than the numerator value. That means that my denominator is Kb, okay, and that should be greater than the numerator value, which is Kr. Okay, that's what the question is asking. Okay, so at higher temperatures than 586, because we determined the switching temperature already, at higher temperatures than 586 Kelvin, the reaction is reactant favored, meaning K is less than 1. If K is less than 1, the backward reaction rate constant should be greater than the forward reaction. Okay, or the forward reaction constant should be smaller than the rate constant for the backward reaction, which is same thing. Okay, so it should be temperatures greater than 586, so which is going to be option A. All right, now, okay, I'm gonna erase some of this so that I can make room for the other ones. Okay, now I'm gonna leave the rest there. All right, now moving on to question 12. What is the value of the rate constant for this process? Now, here's the thing. All right, we are measuring CO2 concentration. Okay, we cannot know the order of the reaction with respect to CO2 just by looking at this reaction over here. Okay, that's the overall. This is the overall reaction. It doesn't tell us the order with respect to CO2. We need to perform an experiment and then determine that, or we can come up with a mechanism to justify the experimental rate law after that. Okay, anyway, so the idea is if you're given the time and concentration data, do this. Okay, always plot these guys. Okay, so we're gonna, in your calculator, we're gonna have a table list, actually 4 lists. Your list 1 would be time 0, 40, 80, 120. Okay, if you want to have 160 as well. And then your list 2 should be concentration, in this case CO2. Okay, and then have that handy. 6.4 times 10 to the power of minus 3, and 4.15 to the power of minus 3, and then 2.67 times 10 to the power of minus 3, and so forth. And then make your list 3 natural log of concentration. Okay, I don't know the values, we have to calculate that. And then your list 4, 1 over concentration. Okay, so the idea is if you plot these graphs, depending on which one is linear, we can determine the order of the reaction. If this was linear, then it's going to be 0th order. If this was linear, it's going to be first. And if this was linear, it's going to be second. That's going to be the goal. Now I'm going to do this on Excel because that's what I have. I have time and CO2 concentration, and then I have 0, 40, 80, and 120. For CO2 concentrations, we have 1 times 10 to the power of minus 2. And then I have 6.44 times 10 to the power of minus 3 for 40. And for 80, I have 4.15 times 10 to the power of minus 3. And then for 120, I have 2.67. 2.67 times 10 to the power of minus 3. Okay, so now I have those values, and then I'm going to create the other list for natural log of concentration as well. Okay, that should be equal to Ln. Select the values. Okay, I made that list. And then I'm going to have 1 over natural log of, I'm sorry, 1 over concentration. Then I'm going to create that list as well. All right, now I have those values. Okay, and I'm going to plot these. Okay. First, the concentration versus time. Let me see. Okay. All right. Now I see that the R squared 0th order graph is not that linear. Okay, R squared is around 0.96. So I'm going to plot natural log now. Oh, that is linear. The R squared is exactly 1. And then I have a slope of 0.011, negative 0.011 for that. And just let you know, my second order. All right, it doesn't want to plot second order. Let me try one more time. Okay, and the second order is not linear. The R squared is 0.9639. Okay, so I'm going to go with the first order graph, which is natural log of concentration versus time graph is linear. Okay, so just to let you know, right, if you plot the natural log of concentration versus time, okay, that graph is linear. Okay, so this is natural log of CO2 versus time. Okay, and then the slope of the graph is minus 0.011. Okay, so the slope of this graph is equal to minus or negative rate constant, which is 0.011, and therefore the rate constant is 0.011. and then it's going to have the units of per time. Yeah, so it's going to be per milliseconds in this case. All right, so it's important that we figure out the units as well. It's the first order reaction. If for first order reactions, we always have per time units. Okay, so we need to keep that in mind. Anyway, that's going to be our answer, and that seems like option C over here. Okay. All right. And moving on to the next question. Yeah, given some mechanisms, and then there are some questions. Okay. Let's see. Step 1. Okay, we are given the steps. See which of these two mechanisms is consistent with the experimental data given above. Okay, so experimental data revealed that the rate law must be rate constant times CO2 concentration to the power of 1. And then we do not know the order with respect to OH minus is still why we don't know that. Okay, so what we're looking for here is the mechanism that tells us that gives us an order of 1 with respect to CO2. That's it. Okay, now let's look at the mechanism 1. Mechanism 1, the slow step is the first step, and therefore the rate law is rate constant times CO2 to the power of 1 times OH minus. That's it. Yes, the mechanism 1 is consistent with the data. And mechanism 2, the rate law, the rate of the oral reaction depends on the slower step, which is going to be the second one. Therefore, the rate law must be rate is equal to K2 times HCO3 minus concentration times OH minus concentration. Okay, but here's the thing, HCO3 minus is an intermediate. Okay, so we cannot use it as it is. So we go back to the previous step where it was generated. We're going to write an equilibrium constant expression, which is going to be, let me use a different color. It's going to be K, uppercase K now. For the rate extent of the reaction, or the equilibrium constant should be HCO3 minus divided by CO2 concentration times OH minus concentration. Right, so you need to show these steps if you have a question like this in your peer response. Now we can write an expression for the CO3 concentration. So it's CO3 concentration, it's a 3 minus concentration based on this must be K times CO2 concentration times OH minus concentration. So if we plug in this value for its CO3 concentration over here, we're going to get rate is equal to rate constant 2 times equilibrium constant times, instead of its CO3, in CO3, I'm going to write this K times CO2 and OH minus. And then I have another OH minus over here. That means it's going to be squared. Okay. Now it is true. Now it has the OH minus to the power of 2, but we don't care about that. The reason is we were only given the CO2 data, CO2 experimental data, and then we know with respect to CO2 experimental data, the mechanism is first order. Okay, so that's all that matters. Okay, so both mechanism 1 and 2 tells us that it's first order with respect to CO2. Okay, so I'm talking about this guy over here from the mechanism 1 or mechanism 2. Okay, and then this is from mechanism 1. It is still first order. with respect to CO2. So both mechanisms are consistent with the experimental data given. So I would select option C. All right, which of the following energy diagrams is consistent with mechanism 1? All right, so the mechanism 1, what's the overall reaction? Is it this? Okay, anyway, so you know what, let's do the overall reaction. Okay, overall reaction, you're gonna need that. CO3 cancels out, you're gonna get CO2 times 2 OH minus, going to become CO3 2 minus plus H2O. Okay, now anyway, what we know is the first step is the slower step. Okay, but we are making bonds there. Therefore, I would expect that to be an exothermic step. Okay, so first step should have a higher activation energy barrier than the second step, but still it should be an exothermic step. Okay, so let's see. So I'm going to eliminate options C and D. Why? Even D, because we have an endothermic first step when it comes to option C and D. Therefore, I'm going to eliminate that. Okay, even though we have a high activation energy barrier for the first step compared to the second step in C, because of the energy exchange or because they are endothermic, I'm going to eliminate them. And then between A and B, I see that I have a very small activation energy barrier for the first step compared to the second step. Okay, this cannot be. This tells us the second step must be slower, not the first step. Therefore, this is not consistent with the mechanism 1, and therefore that's going to leave us with option A. Okay, so the first step is exothermic, but it has a high activation energy barrier. Here's the activation energy barrier for the first step, and here's that for the second step, very small. And then definitely the first step is lower. And then the overall reaction is, yeah, this is the only one that is consistent with those data. Okay. All right, so that is question 14. And 15. You're given data again, so we need to get ready to plot to graph them. Okay, whenever you see data like this, you're gonna most probably have to graph them. Probably. All right. Anyway, the question is, what is the value of the activation energy for the this process? Okay, so here's the thing involved here. So we have what we call the Arrhenius equation, which is relating the rate constant to the temperature. It looks like this: A times to the power of minus EA over RT. If you take the natural log on both sides, you're gonna get minus EA over R 1 over T plus natural log of the Arrhenius constant. Okay, if you plot L and K on the y-axis and then 1 over T on the x-axis, the slope of the graph is equal to minus activation energy over R, and then the y-intercept is natural log of the Arrhenius constant. All right, so I'm gonna plot this and see what we get. Okay, so I'm gonna enter my temperature values first. We have 308, 318, 328, and 338. Okay, and then the rate constant values are 2.26, 2.26 times 10 to the power of minus 2, and then 4.44 times 10 to the power of minus 2, and at 328, that is going to be 8.38, 8.38 times 10 to the power of minus 2, And then the last one, 338, is 1.52 times 10 to the power of -1. Okay, so I got those values. Okay, so I have now, okay, I need to do something here. All right, so I have the temperature and the rate constant values. Now I want 1 over temperature. That would be your list 3 on your calculator. And 1 over temperature values. I'm going to make that a list 1 over the temperatures. Okay, I got those values. Then I'm going to have the natural log of rate constant values in my 4th list. Natural log constant. Then I'm going to select those data. All right, and then I'm going to plot ln k versus 1 over temperature. And let's see what we have. I need the equation if I can. Okay. All right, very good. It looks very linear. Then my slope of this graph happens to be minus 6615.1. Okay, so we should have temperature, right? 1 over T delta Y divided by delta X. Okay, we should have temperature for units. Okay, and this is equal to minus activation energy over R. So minus cancels out to be plus. Now for activation energy is equal to 6615.1 Kelvin multiplied by the gas constant, which is 8.314 joules per mole per Kelvin. Okay, so if you do this calculation, the Kelvin cancels out, you're going to get an answer in joules per mole. Let me do that. 6615.1 times 8.314. Okay, and then that came out to be 54,997. 54,997.94 in kilojoules. You need to make it, this is in joules per mole. To make it kilojoules per mole, you divide by 1,000. That's going to bring it up down to 50. That's gonna make it 54.99 something. 54.99 is essentially 55. So we're going to select option C as our answer. All right, so that would be that's how we could tackle our multiple choice questions in this review. I'll do the pre-response questions on a separate video. All right. Bye, everybody.